have a Constellation of the Month presentation from Rocky tonight. And I think it's Perseus. I may be wrong, but Rocky, when you're ready, you can,
okay.
I'm assuming, share your screen and take over. Thank you.
Okay. Perseus is the hero, and he's been painted and sculptured quite a bit down through the years. The whole story of the his whole story with Pegasus and Andromeda has been very well represented in art. And this is a bronze sculpture by Benito Cellini back in 1545 with him holding the head of Medusa and standing on her body, if you can look down pretty close at his feet. But it's quite a story. Daryl told it the other night on our Observing 101. I don't know if I'll do as good as Daryl, but these are just a couple of representations of old, well, this one on the left is an old atlas, and you can see that Medusa, Algol is the nose of Medusa. And so most star charts do that. They have Algol, when they draw up the sketch to do it, they have Medusa. And on the right is the one from Stellarium's representation. And it has Algol as the as her eye. So that's the way it's been represented on star charts. I'm gonna try to tell you all the mythology of Medusa, of Perseus. He was the son of Zeus and Danae, the daughter of Acrisius of Argos. Acrisius always wanted a son, but his wife just had daughters. And so he consulted an oracle who told him that one day his grandson would kill him. So Perseus was his only grandson, so he locked up, well, this was before that. He locked up his daughter so she couldn't have sex with him, or couldn't get pregnant, let's put it that way. And but Zeus came in and impregnated her. And Acrisius, afraid of killing Zeus's son and mother, put Danae and Perseus into, when Perseus was a baby, put him into a wooden chest and cast them out to sea. And they landed on an island and were raised by a fisherman named Dictys. As Perseus grew into manhood, the king of the island, Polydectes, fell in love with his mother, who was very beautiful. He planned an elaborate ruse to rid himself of Perseus. He had a big party and told everyone to bring elaborate gifts like horses and stuff like that. And when Perseus came, he didn't have anything. So he was kind of ashamed. So he told the king that he would do anything he wanted. So the king was all set, and he said, I want you to bring me back the head of Medusa. So he thought he would get rid of Perseus that way. Athena helped out Perseus to find the Hesperides, the nymphs of the west, who had the items that he needed to defeat Medusa. To find them, Perseus consulted the Gria, the sisters of the Gorgons, who were three blind, perpetually old women who shared a single eye. And if y'all have watched, I know I've seen this on movies before, but I think it's this is pretty much the story of Clash of the Titans. When they denied his request, they shared a single eye among the three of them. They were all blind, but they had an eye that they could see through. And so when they wouldn't tell him, he took their eye away from them. And finally, they told him where the Hesperides were, and he gave the eye back to her. Then when he found them, they gave him a knapsack to put Medusa's head in, and Zeus gave him a helm of darkness to hide. Hermes gave Perseus winged sandals to fly. Athena gave him a polished shield, and then Perseus went on and proceeded to the Gorgon's cave. In the cave, he came upon the sleeping Medusa, and viewing her reflection in the shield, he cut her head off. From the blood coming out of her neck sprang Pegasus. So this is kind of a wild myth, but this is how it goes. He put her head in the knapsack without looking at it. A couple of her brothers or Gorgons pursued Perseus, but he escaped with that cloak of darkness that they gave him. Then he headed back home to take take the head to the king that wanted it. But he stopped by a kingdom where Atlas was the king, and he refused hospitality, so he turned Atlas to stone. So on his journey home, he went by the kingdom of Ethiopia, ruled by King Cepheus and Queen Cassiopeia. Queen Cassiopeia, in her vanity, claimed that Andromeda was equal in beauty to the sea nymphs, or the Nereids. Poseidon became angered at this and sent the sea serpent Cetus to destroy man and beast. The oracle of Ammon told Poseidon the kingdom would be destroyed unless he gave up Andromeda to the sea monster. So he tied Andromeda to a rock and waited for the sea monster. About that time, Perseus flew by on Pegasus and saw the sea monster attacking Andromeda, and he pulled out the head of Medusa and turned the sea monster to stone. He went back and he claimed Andromeda in marriage, and they produced 6 sons and daughters, most of them becoming kings. And I saw different accounts. His grandson or his great-grandson or his great-great-grandson was Hercules. And then on Andromeda's death, Athena placed her in the heavens near Perseus and Cassiopeia. It was a favorite subject in painting and sculpture, both ancient and Renaissance. The chief characters of the legend are Perseus, Cepheus, Cassiopeia, Andromeda, and the sea monster. And of course, we all know them as fall figures in the fall sky. So here's just a couple of, you can't believe how many, if you Google Andromeda chained to the rock, how many different paintings there are of that. But a lot of them painted it. But anyway, that's the legend. So let's get on with Algol now, which is one of my favorites. So Algol is known as the demon star, and it's a eclipsing binary. It has a constant 2.1 magnitude, but except when it's not an eclipse. It dips to a magnitude 3.4 every 2.86 days. And the eclipse lasts about 10 hours. And you can see down here at the bottom of the screen kind of the light curve of it. And one of the variable star requirements or alternate requirements is to estimate Algol over the period of its when it dims. And since it dims every 2.86 days, it does it quite often, but it takes 10 hours. So and you can find the minimum Algol by just Googling the minimum of Algol. And Sky and Telescopes has a thing that'll give it for about the next week when it's going to be minimum. The trick is to catch it when it's at night, because like here you can see it doesn't even come up now until 11 o'clock. So at 8:39 p.m. you can't see it at minimum. You can catch it going out of minimum. But anyway, it's a good exercise. And something else you can do if you look at the map here, and this is from our book, Learning the Constellations. But you can see Perseus. You can see these numbers right here. These are the magnitudes of these 3 stars. So Alpha Perseus is one of the brighter stars at 1.8, and Algol is normally at 2.1. So if those two are pretty close, it's not an eclipse. But if it's dipped to somewhere around one of these 2 stars, you can tell right away just by glancing at Perseus if Algol is in eclipse. And that's, of course, the way, if you estimate it over a 10-hour period, you'd be making estimates based on probably these 3 stars. Here's another one, 2.1. So that one's real close to Algol, this star in Andromeda. So anyway, that's a nice, fun exercise. One of the neat things about Perseus is I like to draw it this way. There's other ways to draw it, but this is the primary way. And you got one arm, his nice long sweeping arm that points to the Pleiades, and another arm that points to the double cluster. And those are two of the most. There's three of the most prettiest open clusters in the sky in this. There's actually four really nice ones, open clusters. So when I think of Perseus, I think of open clusters. So this is the double cluster in Perseus, and it's not a Messier object. It's really bright, magnitude 3.7 and 3.8. It's think about this. It's 7,500 light years away. That's a long way away, and it's still magnitude 3.7 and 3.8. They're both very young, about 12.8 million years. And I'm going to compare it to the Pleiades and the Alpha Perseid cluster. Mostly blue-white supergiant stars, and NGC 884, which is this one, has 5 variable red giant stars that you can see in the cluster. So next time you look at them, be sure you look for the red stars, the red supergiants. This was I built when I was had just gotten out of college. I ground a mirror and built a telescope, 4.4 inch telescope, and all I had before that was a 60 millimeter refractor. And the double cluster was the first thing I looked at, and it just blew me away with that 4.25 inch telescope. And a small scope, I think, is actually better than a big scope on this cluster. And I know the Pleiades is not in Perseus, but I put it in here anyway because it's close, just to give you a comparison. Where the double cluster is 7,500 light years away, this one's only 444 light years away. So the other one's almost 20 times as far away. It's also dominated by a lot of blue luminous stars. And it was formed a longer ago than that one, 75 to 100 million years ago. And something we don't even think about is the Alpha Perseid cluster. Like, we don't think about the Big Dipper being a cluster, but they're actually, I think, going in the same direction, but because they're close. But this cluster is about 600 light years away, and it surrounds Murphak, which is the Alpha Perseus, the brightest star, the one that I showed a minute ago on the chart that was 1.8, magnitude 1.8. And it's I don't guess it's associated with them, but it's close to them at 510 light years away. But one thing that fascinated me is that I don't know how they measure it, but they said this cluster is at magnitude 1.2, which is even brighter than the Pleiades. So I'm going to try looking at it with averted vision next time I try to see it, to see if I think that's right. And it's 50 to 70 million years old. So it's not as young as the double cluster. Then another one that a lot of us have seen, if you've looked at the Messier objects, is M34, which is a pretty bright open cluster at magnitude 5.5. So it's visible naked eye if you have some good skies. And it's about 1,500 light years away and 35 minutes across. So about half a degree across. And I showed that because the next one is going to be totally different. This is, looking at it on the map, you kind of think the little dumbbell is in Andromeda because it's right next to Beta Andromeda, or one of the Andromeda stars, but it's actually in Perseus, and it's the Little Dumbbell Nebula, a planetary nebula at magnitude 10.1, but it's only where the other one was 35 arc minutes. This is only 2.7 by 1.8 arc minutes, so it's very small. It's about 2,500 light years away. And that is the end of my presentation.
Thank you, Rocky. We really appreciate it. I will turn it over to you, Dino, and you can, Chris will help you get your video started on the screen.
Awesome. I hope you don't mind that I just unmuted myself. And present. Okay, so this is my science fair project that I did last year, and I'll go ahead and give a little bit of background, even though I'm going to have a whole background. But this was my science fair project last year at Central High, and I got second place in my division at Central, and I took it to the local regional science fair, so it's all the different high schools, and I didn't win anything, and I was a little bummed out. But to be fair, the guy that got first place in my category made a solar sail that was powered by a flashlight, so that was awesome, and I'm very happy he won, actually. So I'm going to go ahead, and I think that the best way to explain my project is to read my abstract and introduction from my science fair paper, and then everything else I will explain by showing the exact calculations I used to do my project. So this experiment focuses on orbital and physical properties of planets. In this experiment, I created a star, 10 individual planets, and a major moon. Each body's properties and orbits were calculated using a series of equations. These planets and moon were then set in orbit around the star and recorded logarithmically over time for any orbital decay as seen by their semi-major axis. The simulation was run in the program Universe Sandbox. The purpose of this experiment is to demonstrate the mechanics of a solar system and show what it takes to keep this system stable. The hypothesis is that it should be possible to create a stable solar system given the current understanding of planetary motion and physical properties of planets, using a system of equations to define specific properties such as a moon or planet's mass, density, radius, as well as its semi-major orbital axis. It should be possible to create orbits that remain stable over the period of 1 million years. The null hypothesis is that our current understanding of planetary motion is not sufficient to create a system that remains stable over a period of 1 million years. The initial plan was to run it for 1 million years, but by 100,000 years, enough data was recorded to formulate a satisfying conclusion on this test. The data collected showed a system that was not stable, indicating that something went wrong. This does not necessarily indicate the null hypothesis, as there are many factors that could be at play in the downfalls of this model. For this test, the hypothesis is not accepted. More tests should be done in this subject to try and prove the hypothesis. More about this can be read in the discussion section. And now we get to my background information. So essentially, my entire project focused around me using a system of equations to calculate a completely stable solar system. And I did this because I wanted to kind of demonstrate how we can make models to show what we expect when we're looking for other stable planets and solar systems that could potentially be habitable out in the universe when we are looking through data from things such as like the Kepler project and whatnot. And in my introduction, I wrote, one method to understand how habitable worlds work is to use a model. Technology has reached a point in which it is possible to make a model solar system out of mathematical equations. This experiment will focus on that concept, starting with a star, the properties of the solar system, such as the habitable zone and frost line will be defined. Afterwards, planets will be designated or designed with unique physical and orbital properties, each with their own, or one with their own moon system, provided, or excuse me, each with their own, or one with their own moon system. Sorry, I'm a little nervous. Um, Once a stable solar system is put together, it will be tested for its stability and functionality. It is important that orbits remain stable over time, as decaying orbits will cause wide-scale instability throughout the entirety of the system. The system will be tested for a period of 1 million years. And then I restated my hypothesis and null hypothesis. Stars are classified under the Harvard Spectral Classification System. The Sun and other habitable stars are G-type stars as we understand today. And they typically have a temperature of around 5,000 to 6,000 Kelvin at the surface when fusing hydrogen. Necessary properties to fully understand a star are mass, luminosity, diameter, surface temperature, lifespan, and the habitable zone of that star. These findings are used to define the inner and outer limits of the solar system, meaning how close and how far a planet can orbit from the star, and the frost line, which is the imaginary boundary line in which new planets will develop as gas planets instead of terrestrial, meaning rocky. With planets, it is important to define planetary orbits in the solar system in a way that will make sure no planets are too close together. I accomplished this using an advanced calculation based off of the Titius-Bode law, a law by Jonathan Titius, stating that planets' distance from stars fit in a symmetrical orbital pattern. While it later proved to be less reliable, it originally predicted the orbit of the previously undiscovered planet Uranus within 0.4 astronomical units. This calculation takes the first planet after the frost line and multiplies its distance to the star by a constant between 1.4 and 2 until no planet can be placed inside the calculated outer limit of the star. The distance of the first planet after the frost line has its distance to the star then divided by 1.422 until no planet can be placed inside the calculated inner limit of the star. This randomness allows for natural but predictable planetary development, mirroring the findings of the Kepler project. The numbers found in each calculation are the semi-major orbital axis, or average distance from the star. Once the semi-major orbital axis of a planet is determined, the physical properties of each terrestrial planet can be applied. These properties include mass, gravity, radius, density, circumference, surface area, and volume. In order to achieve realistic numbers, each of these properties will be calculated relative to their properties, or to the properties of Earth. Planetary orbits can be defined using the semi-major orbital axis and picking an eccentricity, how ovate the shape of the orbit is, meaning how much it looks like an oval. Eccentricity is defined under Kepler's first law as being between 0 and 1, 0 being a perfect circle and 1 being a straight line. Planets usually have an eccentricity of between 0 and 0.2. Other orbital properties to be determined are the periapsis and apoapsis, otherwise known as the perihelion and aphelion. This is the closest and furthest a planet will be from the star in its orbit. Orbital period, the time it takes a planet to perform one orbit. Velocity and inclination, or the tilt of an orbit on the orbital plane, usually relative to the habitable planet of the system. For gas giants, all the same physical properties can be calculated in relation to Jupiter instead of Earth, with a few exceptions. Gas dwarfs, or gas planets smaller than or around the same size as Neptune, will have their properties calculated in relation to Earth due to their small size, while their orbital characteristics will still be calculated in relation to Jupiter. This is done due to the difference between gas planets and terrestrial planets, but all the same base equations are used. So, now that sounds like a lot of useless information at the time being, but actually, it's quite useful when you look at the equations themselves and how they are applied. So here is my decent handwriting from my notebook where I did all of my equations. If you look on the left here, this page is where I wrote down all of the different formulas for a star. So I have them color-coded because I thought it looked nice, but you can see that using just the mass, and what I did is instead of saying 2.536 times 10 to the 30th power kilograms, I instead based it on solar masses, with the sun being one solar mass, and my star was 1.275 solar masses, meaning it was 1.27 times more massive than the sun. You can take that and use that mass and plug it into all of these equations to find different properties of the star. So, for example, what I would do if I wanted to take and find the, let's say, we'll go for the habitable zone, otherwise known as the Goldilocks zone. All you really have to do is take the mass of that star to find its luminosity by essentially taking the mass and putting it up to the power of 4, which sounds less complicated than it should be, but somehow is completely correct. And you find that the luminosity of this star is 2.643 roughly, meaning it is 2.643 times more luminous than the sun. Then you take that luminosity and you square it off, and you can find the full Goldilocks zone by taking that number that you just found and multiplying it by 0.95 and by 1.37, and that would be the inner and outer limits. So the inner and outer limits of my habitable star are 1.545 AU to 2.22 AU. And then I had to place my planets. So first things first, I need to find the inner limit and outer limit and frost line of my star. In order to do that, all you do is take the mass and multiply it by 0.01. That gives you the inner limit of the star, which for me was 0.1275 astronomical units. And the outer limit is you take the mass and you multiply it by 40, which for me was roughly 51 astronomical units. Then the frost line, you multiply it by, or you take the luminosity and you take the square root of the luminosity and then multiply that by 4.85, which for me was 7.88 astronomical units. And those are very important numbers because that is the entire range of the solar system. It determines how close, how far a planet will be, and when you will stop seeing rocky terrestrial planets and start seeing gaseous planets. Now that looks great on paper, I'm sure. That's a bunch of numbers, that means a lot. But I have, later on in this presentation, a picture of all of this actually in a simulation where you can see all of the individual planets in their orbits. And it's very rewarding seeing that and knowing that you did all that work. And here's how I found the properties of each planet. Again, you can see that I color-coded the mass, gravity, radius, density, circumference, surface area, and volume. And here are the equations that determine those properties of each planet. And I have a lot of scratch paper with a lot of scratched out numbers that I did for each of these calculations before I put them in my notebook. But it looks a lot nicer when you just see these right here. And this is all the properties of each planet. So this is its mass, gravity, radius, density, circumference, its surface area, in case you were wondering, and even its volume, which you probably don't ever need to know, but hey, you can do it. So why not? It's just cool to show off that you have the ability to do these things. And this is my first first six. And you can see that I named them all after famous astronomers, or in the case of Brahe, defamed astronomers. And that's what he gets for having a brass nose. And then we have my terrestrial orbits, and you can see I screwed up on eccentricity and had to respell that. But I have all of the different calculations for each orbit of each planet, and you can see that all I did was I took the semi-major axis of each planet and the eccentricity to find its periapsis and apoapsis, meaning its closest and furthest approach, its orbital period, velocity, and I picked an inclination of anywhere between 0, meaning it's just completely flat on the orbital plane, excuse me, and 3, so 3 degrees up. And here's what it looks like for each planet's orbits. You can see Brahe was my habitable planet, so it was orbiting at about 1.96 AU, and its periapsis and apoapsis do remain within the limits of the habitable zone, so its temperature is just suitable for life, which is perfect for what I wanted to demonstrate. And here's the same thing, but for gas giants, and I clumped these both together since I had demonstrated pretty well how I do the other stuff on the previous pages. And you can kind of see that it's all basically the same equations. The only difference is that the orbits were done in relation to Earth's orbit, but the properties were calculated in relation to Jupiter's properties, just because they're bigger and they're less dense, so get some more accurate reading. And I have Newton and Sagan here, so here's their properties and their orbits. Give a second to read through this. I know it's a lot of numbers. They're very interesting to look at. And Aldrin and Armstrong. And all the same stuff, their properties and their orbits. Now, that's all well and good, but again, this is just a bunch of numbers, which doesn't look as rewarding as this does. And these are my solar systems after my solar system after I inputted all of that information into the program Universe Sandbox, which is a program that is designed to simulate the basically the effects of gravity on a solar system. And what they do is I'm having a real hard time explaining this. I'm sorry, I'm a little bit nervous. But essentially, the program takes all these properties and it simulates gravity. So you can see that they all have an orbit, and there's a little bit of a trail, which I made sure to keep the trails on in the simulation, just so you could kind of see how they move in a mostly circular fashion. And on the left, you have the full solar system, and on the right is just the inner parts of the solar system, since the inner solar system is a lot more compact than the outer solar system due to the nature of how the planets are placed. And I also included a picture of the habitable planet that I designed, just because I thought it looked real nice and photogenic. But yeah, so that's my project, and I basically created a whole solar system using a bunch of numbers and equations, and it was the nerdiest thing I've ever done, and by far the most fun because of it. So what went wrong? Well, I did state earlier that my project didn't exactly go as planned. Now, I hate to admit it, but that's true. However, I don't think it's necessarily my fault. And I know that's a bold claim, but theoretically, all of these equations should create a stable solar system. However, it didn't. And my biggest, or my most, I think that the most likely explanation as to why that this didn't work is due to the program I used. This is a very reliable program, and it does do a very good job at simulating gravity and orbital mechanics, but it can only do so fast. And I wanted to run my program for 1 million years, which is a big goal, meaning that I would have to be running it at a very high speed, so like so many days per second, so many years per second even, and that's a big task for a computer to take on. And I think that the biggest problem is that this program, the faster you run it, the more calculations it's having to do at once to keep the simulation running smoothly. And because of that, every so now and then you might get a little bit of a latency issue or a lag issue, and it might accidentally skip over or miscalculate something. And over time, that adds up. And so that could explain why some of the orbits just didn't remain stable. It could also be that I just made a wrong calculation here and there on my paper, but I fact checked this over and over again when doing it because I wanted to make sure it worked, and it still didn't. So my assumption would be that my computer just isn't good enough to really run this at such a high speed for so long, because my computer was on for a week straight just doing calculations, and that's probably not healthy for any computer. Like, I don't think anything short of a supercomputer could really, really knock this out of the park and get every calculation like right, running it so long. So because of that, it just didn't work. And I think that's part of why I had such a hard time trying to explain it to a judge in such a limited amount of time, ignoring the fact that he talked more than me. But yeah, so that's my project, and I had a lot of fun doing it regardless of the outcome. And I guess I'll leave it open for any questions that anybody has.
Wow, thank you, Dino. If you have questions, go ahead and ask those. I'm assuming Chris can unmute us for that.
And I apologize if I didn't explain that the best. I've never really done something like this before.
You did a great job.
Thank you.
So Dino, do you think possibility you had too many planets? If you would use fewer planets, do you think you would have had better stability?
So actually, that is something that I did go over in the discussion section of my paper, is the idea of the fact that the solar system might have just been overcrowded. However, I took some time to think about this to myself, and this is relatively underpopulated due to the sheer size of the solar system. So this is a much bigger solar system in general, and just like sheer size between the inner limits and outer limits of this solar system when compared to ours. And we have 8 planets, we have millions of asteroids, we have like hundreds of moons of planets, there's all the Kuiper belt objects and even the Oort cloud. And our solar system is still somewhat stable. However, this solar system that I calculated that only had 10 planets and 1 moon on 1 planet, which I guess I forgot to talk about, but somehow that was less stable. So I just don't see it being, and I just don't see it being overpopulation of that solar system, considering none of the objects were ever at any point too close to one another, or theoretically should have been ever too close to one another. But I do think that that is something to maybe consider, for sure. It's a possibility. I just don't think it's a likely one, personally. And I think I have justification. All right. Any other questions?
I wanted to point out to everyone that at the bottom of their Zoom application, there's a reactions button and there's an applause. So let's all give
You
Dino
don't
a
need to
hand.
give me any
Let's all give Dino
applause.
a round of applause.
All right. Thank you. I appreciate this. I
Oh,
didn't.
Do we have, go ahead.
Yeah, do you have time for another question then?
Yeah, absolutely.
All right. So I'm curious about the program, well, I don't know, whatever sandbox that was.
Universe Sandbox. Yeah.
Universe Sandbox. Okay. So do you know, is it solving Newton's equations or is there some simpler
Yes. So
approximation?
I do believe that it runs almost purely based off of solving Newton's equations when it is calculating for orbits and other properties of planets. And when I went in and I could actually, what I did was I took, it has a whole database of known planets that we have found through the Kepler project and their properties and their like density and mass. And what I did when I placed my planets in is I took one that was similar to the planet that I had calculated, and you can actually go in and adjust their density and their mass and whatnot. And when I would adjust the density and the mass, it automatically changes the planet in the system. And when I would just change like the density and the mass alone, all the other properties that I had done through my calculations changed in the system to the ones that I had done. So I believe that that shouldn't be a problem. And the same thing for the orbit. So like when I put in alone the inclination and the semi-major axis, it automatically, and the eccentricity, it automatically showed the exact same periapsis and apoapsis that I had found when I did my equations. So I believe that is how it works. At least I would assume so, considering it found basically all the same things I found.
Well, having run simulations before, that just kind of brings up two questions. You said you sped it up. If you're solving Newton's equations and you speed it up, you must be making your time step a little coarser. Do you know if that's what you were doing? Yeah, you were doing that. Well, I can tell you that'll lead to instabilities.
That's exactly what I assumed had happened, is just because, you know, the more you speed it up, the harder a time the computer has trying to keep up with the demands needed to do all these calculations in such a short period of time. That's kind of my assumption as to why it just didn't remain stable. But honestly, anything short of a supercomputer is going to have a hard time keeping up with that sort of demand. So it's it didn't play out the way I wanted it to, but I still do believe that this is a stable solar system. I just think either the program or the computing power needed wasn't there for me to prove it.
Yeah, that's entirely possible. Let me ask you one other question. Did you initialize it? I mean, how did you initialize it? In a simulation, the starting conditions can be very important in terms of stability.
That's true. So like depending on like the age of the star, you mean? Because
well, its initial position.
Initial position. That's also true, because obviously I did not take into account the like different what's it called? Argument of something one another. It's just basically where on the X, like on the X and Z and Y axis everything is. All I had was the
right. Yeah, you have your initial conditions, and if typically a program will randomize it, and So I don't know if that could be some kind of problem. Probably not in a truly stable system. But
I would assume that it shouldn't be a problem, although I guess computers can be a little wonky sometimes. So maybe
Well,
it was, maybe it wasn't. I don't
one
know how
thing
I would prove that.
one thing you can do is model our solar system. I guess you couldn't do all
So
the minor planets and stuff and run that and see if it's stable with
So
your time
actually,
speed up.
when you first load the game, it has the very first thing you have is a already pre-built model of our full solar system with known asteroids and Kuiper Belt objects and all of the planets and all of the planets' moons. So I could do that and just see if that remains stable. And I would assume, excuse me, I'm so sorry. I would assume almost immediately that it would not remain stable, just due to the sheer number of objects. But that's probably worthwhile doing, just to prove my theory.
Well, it's interesting. I think running a simulation like that is very informative. Uh,
Yeah.
there's two lines of of learning. One, you learn about how to actually conduct the simulation, and then you learn about the physics of the solar system.
Hmm.
So
Absolutely.
it's a great experience. I enjoyed your talk.
Thank you. I appreciate it.
Are there any more questions? Well, Dino, thank you very, very much for your presentation.
Absolutely.
It's informative and impressive too, to see that. And Rocky, we appreciate your presentation on Perseus. That's all the formal meeting that we have for tonight.